Hi, welcome to Desert Island Science, a series of podcasts that probe the minds of pioneering researchers in science and synthetic biology. My name's Amy, and I'm a contributing reporter from the 2016 Stanford Brown iGEM team. This podcast is coming to you from Palo Alto, California. In this episode, I'll share an interview that we did with an extraordinarily accomplished guy. Dr. James Head is the Louis and Elizabeth Shirk Distinguished Professor of Geological Sciences at Brown University. He was an investigator on several NASA and Russian space missions, and he's currently co-investigator for the NASA Messenger mission to Mercury and the Lunar Reconnaissance Orbiter. We were lucky enough to have him visit us in our lab in July. We started our interview by asking him to tell us a little bit about his career at NASA.
Sure. My first job out of graduate school was to work in the Apollo lunar exploration program. I worked on a variety of different things. Basically, I looked at possible landing sites on the moon. So we didn't know where we were going exactly. Safety was a big concern, but we wanted to explore the moon as well. So what we ended up doing was trying to look over the whole moon, particularly the near side, and figure out what geological questions there were and what we could do to answer them. Then we worked on crew training. The astronauts, most of them, virtually all of them, were not geologists, and most of them weren't scientists. They were test pilots, which is exactly what you want when you're sending a spacecraft to the moon that no one has ever flown before to a place no one's ever gone. And yet they were incredibly highly motivated students, amazing. Okay, so it was just wonderful to work with them. Teach them a lot of geology, take them in the field all over the world, and then we would then choose a landing site and we would decide what we wanted to do when we get there. It's one thing to go, I want to go to this place on the moon, but what are you actually going to do? What are your goals, your objectives, and how do you map those out into a plan to explore? And then we'd work with the astronauts in training for those and prepare them for that, and they were, totally excited about that, of course. And then we would be in mission control in Houston when they were on the moon. And we usually go to the Cape, watch the launch, then head to Johnson Space Center, and then be there during mission operations. And then when they came back, we'd help unpack the rocks and analyze them. So that was my first job, which is great. It's hard to go uphill from that. But then we went on to explore planets. Okay, so after that, I worked in mostly planetary exploration missions to Mercury, to Venus, to Mars, to the asteroids, to outer planet satellites. And also worked a lot on exploring different kinds of terrains, one of them being Antarctica. I've had 5 field seasons in Antarctica looking at 2.5 months a season, a year, and looking at basic environments that are very much Mars-like and trying to understand how climate change and also active volcanoes, and also worked on a seafloor and deep-sea submersibles exploring that part. It's very similar to Venus because the pressure is so great that you can actually figure out how volcanic eruptions might work on Venus. So that's kind of what I do.
We next asked Dr. Head if he could give us just a few more examples of the types of questions he attempts to answer via planetary research.
What we do on the Earth is to try to basically understand how the Earth works. And that's why we go to the bottom of the ocean floor, we look at it from space, we go out and bang on the rocks, we look at the Antarctica and so on. And what we find is that the Earth is incredibly dynamic. Okay, it has plate tectonics, which means it's a global part of the thing is being renewed, etc. And it also has huge amounts of water and erosion. So the good news is we can actually watch all this work. I mean, I don't have to tell people in Southern California that things are moving here. Okay, so Northern California either. And so the deal is that we end up understanding that the Earth is really dynamic, but the bad news is most of the early geological record has been completely destroyed by that. So we know what the Earth is like today. We know what the Earth is like for the last 10% or maybe 20% of its history, but the first half of solar system history on the Earth just isn't preserved very much. So there's rocks here and there, but not really a lot. So how do we find out the childhood of the Earth? We want to know where we came from, what the formative years were. We want to know what's going on that brought us to where we are today, which helps to understand where we're going in the future. Without those missing chapters, it's like you pick up a book and you're reading chapter 19 or 20 and you have no clue what was going on. So we have a lot of clue what's going on now, but we don't know what's going on in the past. So Where do we find that record? Well, we have a lot of planets in the vicinity, which we can go look at, and as luck would have it, they're smaller than the Earth, which means their crust and lithosphere is stabilized, and so they actually preserve the record of that early history. So my quest has been to try to understand Earth-like planets, the Moon, Mercury, Mars, and Venus, and how they relate to the missing chapters in Earth history and how they all work together, if you know what I mean. And so we learn so much. You know, we learn about the huge numbers of impacts that were occurring in early Earth history, in early history. We've learned that the Moon actually came from a Mars-sized object hitting the Earth, and it's all the ejecta from that. You know, it's like if I wanted to know you, I would ask, you know, so tell me about your childhood, and I would want to know about traumatic experiences that might have, you know, shaped your worldview. I mean, imagine a planet being hit by something half its size. That's a traumatic experience. So, what, you know, does that make us different than Venus, for example? You know, I mean, these are kind of critical things. So you can look at it as a psychology of a family of planets, basically.
Cool. We next posed the following question. What did Dr. James Head think were the most important space exploration objectives of our time?
To me, the most important exploration objective in space is the study of the conditions that might have formed or led to the formation of life, or even been in an environment in which life might have been conducive to the formation of life. So I think exploring environments which are in members on this possibility is really important.
Yeah.
You know, Earth is incredibly contaminated with life, so to speak, and it's really it's hard to find a place that there isn't life. So life is so opportunistic that it occupies almost every part of the system. So we need to be thinking about where did it start, how did it start, what are the processes that really led to the promulgation of life and its spread. And you know, we have a lot of laboratories out there. You know, Mars is one, Venus is another. Venus Venus has not always been the way it is today. It's a furnace, okay, very high pressure furnace, but it had water in the past, and why did it get to be the way it is today, and what happened to life if it started there? Europa, you know, we have an ocean on top of a planet, and it has an ice crust, but then all kinds of things are going on underneath, and this is, geez, you know. So, you know, if we find there's no life on Europa, no life on Mars, then what does that mean? Does that mean you know, the conditions were unique here on the Earth? If so, what were they? And we also might find that, you know, we always think about searching for life on Mars, and, you know, I mean, think about the fact that we know the conditions on early Mars were different than they are today, and likely could have been conducive for the emergence of life. And we also know that there's a large number of impacts that occur, and they eject material out, and it goes into space. And we know we have Martian meteorites. We know we have rocks on Mars that have come that way. So what happens if you wake up in the morning, you look in the mirror, and you discover, oh, a Martian? You know, maybe life started on Mars, a rock got blasted off, ended up in an ocean that was sterile, and then essentially that was the beginning of life on the Earth. I don't think, you know, that's certainly a plausible idea. So those are kind of important questions, you know. I mean, wouldn't it be great if we were Martians, for Christ? It'd just be incredible, you know. But we don't know the answer, and so we really need. That's one of the biggest questions for me. I think the origin of the planets is another one. So what are the conditions that led to the differences we see, and what are the starting conditions? These are really important things. And astronomy now is, you know, in the last 50 years, our solar system planets have changed from astronomical objects to geological objects. So I'm a geologist, I'm not an astronomer. So we get to go there with humans and, you know, robots and things like that. But astronomers have now moved on to look at exoplanets, planets around other stars. And oh my God, you know, when I started my space career, it was a debate about whether there were any other planets around other stars. I'm going, you know, really? It's like saying, oh, I don't think there's life elsewhere in the cosmos. Really? How, you know, that's, how would you know that? I mean, you know, and so now we're discovering more than a planet a week, for crying out loud. And so that's the new, you know, so now we're doing, from comparative planetology in our solar system, we're doing comparative planetary systems. And we're learning a huge amount from that, you know, that Earth, our solar system is different, but then there's a wide variety, you know. So those are a couple of the things that I find interesting.
So then my teammate Julia asked him, what might that life look like? Are we looking for little green people, or are we looking for bacteria?
I think it's a good question, what life forms would look like elsewhere in the cosmos. I mean, I don't think we know. I think people have argued, like Carl Sagan has argued, that it's very likely carbon-based, not silicon-based or things like that. There's a variety of good reasons why that might be the case, but maybe we're looking at the wrong thing. Maybe we're thinking, not so broadly. I think I would say, based on our planet, I would argue that the first kind of life we might encounter would be more bacterial-like. Why? Because, I mean, humans are a marginal species. We're really a marginal species. A couple of little volcanic eruptions, a big impact, it's over. But bacteria, they rule, you know what I mean? It's like they're so incredibly able to withstand and accommodate things that I think that's more than likely the versatile, quickly reproducing, able to adapt to different environments with multiple generations. That'd be my bet. That'd be my bet. And evolution is non-deterministic. So the idea that they might look like us, I think, is insane. I mean, it's non-deterministic. Think of all the different specific steps that had to happen, not taken, had to happen, just to get us. And I mean, we don't even know those. But if we did know those, there's no way you could repeat it. There's no way. I think so. I'm excited. I hope we recognize it when we find it. I mean, I think that's the root of the problem. Maybe people say, "Oh, if life was out there, it would have contacted us." Well, they're not stupid, probably, but I mean, maybe it has. Maybe life contacted us because we're Martians. Maybe that was the original contact. And so I think it's a really good question. And one which I think doesn't, in my view, doesn't have a simple answer. That's part of the excitement, too.
So then we asked, how does synthetic biology help us in all this?
I think synthetic biology, there are two aspects to me that make it really exciting. The first is that it's just a completely new frontier. Completely new frontier. It's like discovering that there are planets out there, maybe discovering that we're not the center of the cosmos, okay? Whoa, that rearranges your thinking. And it's like we talked about, in the sense that Albert Einstein was purported to have said at the advent of the nuclear age, when the first nuclear weapons were detonated, that, well, everything's changed but our way of thinking. And it was a very prescient statement, because what he meant was that, well, everybody knows that happened, but nobody has a clue as to what that really means. And I think it's the same thing. Not everybody knows about synthetic biology, but I can guarantee you, that's going to change everything. Everything. Just like the invention of computers and things like that completely changed everything. So I would say that the beauty of it is that that it opens up such incredible opportunity in so many different ways. And when you think about, for me as a space scientist, the ability to do things with synthetic biology that would help us to undertake exploration that we would never have been able to before, because we don't have to ship steel girders to Mars to build a habitat. We can make bio bricks, and for something you might be able to hold in your hands, you might be able to produce building materials with native soil so you could go somewhere and do some things you'd never be able to before. So I think that's, to me as a space scientist, that's really, really incredible.
We then asked, if we were to have a biological sensing balloon, how might it be useful to planetary scientists, and where would it make most sense to send it?
So for Mars, a biological sensing balloon would be just incredible, because there's so many different environments on the surface of Mars that vary as a function of temperature and pressure. And so also there's a complete 4.5 billion years of geological record laid out there. So as a geologist, I would start by saying, gee, we really need to understand the atmosphere, but we also need to explore these various environments. For example, we detect methane on Mars. What does that mean? Is that rock forming? Is that biological? Where is it exactly? It usually diffuses into the atmosphere. We make a general measurement. We don't have a huge amount of directionality at the present time. So, having a bioballoon that could go through the atmosphere, make temperature, pressure measurements, just simply from the point of view of understanding the climate, that's incredible, okay? And wind patterns and things like that. But the idea is that, you know, if you're going over, I would design traverses which went over different age terrains, you know, different geological environments. For example, we have evidence for tropical mountain glaciers that are 200 million years old. Well, if there was ice there and water there in the equatorial regions, you know, that's an environment we have evidence for flowing water in the relatively recent, maybe the last 100,000, 200,000 million years. You know, that would be a place. Absolutely send bioballoons over that. We have evidence for very ancient valley networks, open basin lakes that are the size of Lake Baikal and Caspian Sea, for crying out loud. They're big. They're empty now, but you know, they're open basin lakes because a stream flows in, fills it up, goes out the other side. So you know it had at least that much water. That's where I'd go as well. So Mars is a good one, but of course, you know, Venus, I mean, what is in the Venus atmosphere? You know, if the climate changed and it adapted, is it possible that, you know, there's biological life, so to speak, at clement parts of the upper atmosphere? Maybe, you know, our little bacterial friends figured out, oh, we got to get moving here, and they evolved to something that's stable on, you know, dust grains, or just simply, you know, complex molecules or something like that. And then, yeah, and Titan. Oh my God, yeah, Titan. Yeah, it's incredible.
Next, we asked, what would be some of the challenges of sending such a balloon into space?
I would say the challenges of sending biological balloons in space would be, the things you want to think about are, of course, the capability of the balloons, their ability to be controlled, what they could do, etc. But then there are also issues like contamination of environments. There are issues such as, you know, planetary protection. I mean, just contamination with organic-based materials, but also, you know, living organisms and what that might do, etc. So those are all big questions. But I think that those are on everybody's mind, so it's not like this is going to be a big surprise to anybody, and I think it's really important to press on, so to speak.
Finally, we asked Dr. James Head, how does one compose the ideal scientific team?
Yeah, I think to get an ideal synthetic biology team, I would say the first thing you need to do is go read a couple books in team building and leadership. And you know, I mean, I see this all the time. We form teams all the time. Research teams, we form spacecraft teams, we form instrument teams, etc. And there's a common misconception on a lot of scientists' parts that everybody has to know everything. You know, well, if you don't know that, if you don't know about what I do, then teams are teams. Okay, they're not collections of individuals, all of whom know the same things. You know, if that were true, you'd only need one person. Okay. But the truth is, you need mutually reinforcing and mutually supportive kind of skills. That's so important. You also want to be careful, and this is critically important. You can design on paper the best possible team, but if two of the team members are hypergolic, you know, you're dead meat. Okay, do you know what hypergolic? So hypergolic is like in rocket propulsion. If you mix two fuels together, if they're inert, there's no problem. But if they are not, they explode. They're called hypergolic. So that's like getting two personalities together that are going to fight each other, and you're going to have an explosion on your hands. So you want to be careful about that sort of thing too, because that can destroy everything. And then, of course, the disciplines. You need a couple of different kinds of things. You need people who are young, enthusiastic, and don't know that things can't be done. That's critically important, okay? Because they can be done, okay? You know, we went to the moon in less than 10 years, a lot of times. Think about that, okay? Just yesterday, you know, was the anniversary. It's like incredible. And so that's part of the ingredient. And then, of course, people who are expert in a range of biological backgrounds, I think. But most importantly, you need other perspectives, too. Like, this is why a lot of our interactions at Brown between planetary geosciences and biology and, you know, is so important, because we have some different perspectives and can provide those. And I guess the last thing you need is to complement the people who, all of whom don't know it can't be done, is the professional doubter. Okay, this person will be a pain, okay, but you need somebody who's going to ask critical questions, okay, critical questions. And maybe not a core person necessarily, but somebody that comes in and you know, is demanding to show that you can actually do what you say you're doing, or That's critically important. We had one of those in Apollo, and it was a pain, but critically useful. Critically useful.
And that's it. If you'd like to hear more from leading scientists on the future of synthetic biology, make sure to check out the other podcasts in Team Exeter's series, Desert Island Science. From Palo Alto, this has been Amy of the Stanford Brown 2016 iGEM team.